All right, so today, as promised, we'll take another tour of the process switching and talk a little bit more about context switches and context and all this in general. There's also a new homework to discuss, and we'll take a brief look at my homework 4 solution. Maybe we'll start with the homework 4 solution, so I'll take a pause in the recording right away.
So is there ever a possibility to tie that into the actual file descriptor so that if you have a different process re-map it, then they actually share the same address instead of just making a new one into a new calendar?
Yes, okay. So, yeah, in a normal Unix, if you map in a file, you only ever get one physical copy of the file. Unless you map it in, it's called private. There's a flag called private, and then you get, and we'll do that in the next homework actually, what's called a copy on write mmap. So everything is mapped in, shared copy, but then if you try to write to it, you don't actually get to write to the shared copy. Then you get your own little copy of that page that you were writing to. But anyway, if you wanted to get this thing to work with multiple processes and not double up the memory, then you'd have to keep track of, for each open file, where it is in memory. And so we already have the open file. Let's see. I'll just use this one. Is it in file? Let's see. Ftable, right. So these are only for files that are currently open. Those are the ones that make sense. And a struct file is basically right now an inode pointer and then the index and maybe some other things for pipes and such. So what you could do is then put inside of this struct file, you could have a little data structure that says for each page offset into the file, where is it in physical RAM? So then when a user comes and says, or a process comes and says, I want to mmap this file, well, we already are reusing this struct file. Wait. I lie, that's per process. We'd have to keep it in the inode then. It's kind of ugly too. No, that's all right. Yeah, so we could keep it in the struct inode. And then when you want, well, say in the lazy where one process says, oh, I need that page from this file, we first check in that index to see if we'd already have it mapped in somewhere in memory. In that case, we just grab that instead of kallocating. But that gets a little complicated. It's actually an excellent segue into our next homework. We're not doing that swapping after all. I decided we'll stick with the homework we used last semester, and it's called dedupe. So in this case, well, we're not actually using multiple processes because it's a bit of a pain, but what we're doing instead is we're trying to save some memory. So if you have many pages in memory that have all the same contents, we have a little sysdedupe system call that basically merges all of those pages. They used to use 10 physical pages, but they were all full of ones. And so they may as well just point to a single one. All 10 of them point to a single one full of ones. And now we're sharing saving 9 pages of memory by sharing just a single one. This is similar to shared memory in processes. Basically, you have this problem of how many processes are currently using this page. When you close a process, can you free those pages? You have to deal with memory management a little bit differently. Right now, I don't know if you've seen this, but let's see in vm.c pages. Oh. Free VM, yeah. So basically, this is how we deal with memory management right now. Processes kalloc whatever they want, as long as they stick it in the page table. And then when the process dies, well, everything gets freed right here. And then all of their page table entries. Right. That's pretty convenient, unless you have a shared page. Now, if you have a shared page, you can't go and free it, because then it'll end up in the free list and someone starts overriding that with other stuff. That's going to get really nasty. So now we have to handle how many pages how many users exist of any given page, and usually you do that by reference counting. In garbage collected languages, there's different ways to do it. Like you could run an actual online garbage collector, check all the pointers from the heap and so on. I don't know who's seen garbage collection before. Okay, a few of you have. Cool. In 361 or?
Yeah, I think so.
Yeah, very good. I made that homework. Okay, so you can do that. Of course, in C you can't really do it because we don't have proper types in C. But in Java, you know for every piece of memory, you know what's actually there. You know that there's a pointer there. If it's a pointer, you can follow it and see what else is wherever it's pointing. Anyway, in the case of the kernel, we keep it a little simpler. So we just keep track for every page, a huge array for every page in memory, every physical memory page, to see how many users are there of it. And once that number reaches 0, well, then we're free to add it to the free list. All right, let's take a quick look at the homework 5. Basically, the job is we have a simple program that allocates some memory, and then maybe does some writing to it. But most of it is very simple. Like it's a bunch of zeros, all over memory, or a bunch of ones. At some point, the program calls dedup, and then we're supposed to discover that pages 3, 4, and 5, they're all zeros. Why don't they all share one page? So then we remap, we manipulate the page table so that they're all pointing to one page, and then free the other two. And that's great. So now we've saved some memory. Of course, the problem then becomes, what if you start writing to one of those pages? It's going to happen if you write to one of those deduped pages, you think? No page fault. No. So we've just mapped the pages in. So actually, let me maybe just to make this a little bit clear, we may as well have a drawing. Is this? No, that's not it. Where are my drawings? Here. Right. Yes. I am recording it. Yeah. Thank you. Okay, I'll copy one of these little stacks. All right, so here's our heap. All right, and we have this is supposed to represent the hex value in an entire page of memory, right? Okay, that's enough. And so so here we're using 5 pages worth of memory. These are not even allocated. We're using 5 pages worth of memory, but these are full of zeros, all of them. So in our virtual page table, we could instead of having just a bunch of arrows that go like that, or if these represent physical memory pages, these are virtual memory pages, instead of going like that, we can just go like this, and now have 3 page table entries pointing at a single physical memory page. Now the process comes and tries to write to, say, the middle byte over here. Then of course that byte is going to show up, that value is going to show up here and here and here, right? Because we've mapped in the page 3 copies of the same page. So this, in our case, this happens in several pages within the same process. In a more common situation, it would appear in multiple different processes. Right? But the problem is the same. Of course, that's no good. No programmer would expect, when you do one write, that this would appear in 3 different places. We can't have it that way. So what do? How do we solve this problem?
I was going to say make it read-only, but that's not a good thing to do.
Why not?
I don't know.
All right, anyone want to volunteer? Why is this a bad thing to do? Make it read-only. We got a hand up there.
Well, I mean, you just make it so you can only read from it, and then if someone tries to write to it, then you copy it to another location and write to the new one. Right?
That's making it read-only. We were looking for a reason why it's a bad idea. That sounds like it's a good idea.
I mean, if it's only read-only and you can't write to it all,
Oh, okay, right. If we make it permanently read-only, that's a bad idea. Yeah. So let's make it temporarily read-only. That's actually the right solution. So, so we just, in all of these mappings, we have a pointer over here, but you know, there used to be read-write. They used to have the PTEW flag set, but now we just clear that flag. So now you can't write to these pages. And then, of course, when we try to write to the page, we get a page fault. And then we have to fix it. So the fix, as you propose, is we make a new copy. So we take this and put a 0 over here. Like we copied all the contents of this, copied it over here, and maybe we try to write to this one in the middle. So I'll just take that one, and we point it to over there, and now we're good to go. Return. Just make sure that this entry now is read-write. So it's okay for it to be writable as long as there's only a single copy, a single pointer to that one page. Right? And then it can go ahead and everything will be fine. So yeah, that's about it for the homework. The tricky part, I think, let's see what's in the. I think I may have helped out with this. Let's see. Okay, release. Aha, look at this. Man, that was nice. So actually updated kalloc a little bit for you guys. So instead of a k-free and a kalloc, like we used to have, we now have a k-release and a k-retain. And retain means, oh, there's now another user of this page. So if you alloc the reference count, let's look at this here, frame info. Oh. Here's the frame info. All right. So we have a huge array, or kind of big array at least. For each page, we have a struct that says what's the reference count of this page, and also I use the checksum. All right. So this frame info says how many users of this page at the moment. So then if you kalloc something, naturally kalloc will set it to 1 here, because it just came off the free list. It used to be 0, so they'll set it to 1. And then if you use it again somewhere, you put another pointer to this page, well, then you're supposed to k-retain it. And that means if you've used maybe in Objective-C, you may have seen this a lot, release and retain, if you do any iOS programming. Basically, it increases the reference count on this page. And then there's k-release, which decreases the reference count. And then if it ends up being 0, well, then we also free it. Because now there's no other user of this page, so we can add it to our free list. All right. So, of course, this is all good, but it also required a lot of changes in the rest of the code. So, well, that's not so many. Really? Well, maybe that's fine. Seems to me like, okay, I'll have to take another look at this just to make sure. I was merging this with our new master, and I may have missed one or two. But either way, throughout the kernel, now you can't really k-free it. In any case where you may have k-retained a page, you can't use K-free because there could be maybe two copies. So yeah, we're not very likely to be, these are the PDP and the PML4, we're not very likely to be reusing those, right? K retaining those, or maybe some places. But in general, it's the kind of the user pages that we are manipulating, and so those are the ones that need to be K-freed, K released and K retained. All right. So so anyway, what you'll want to do is scan through all of the user pages and look for copies. But this could be pretty slow. We're allocating, I think in this program we're allocating 1 megabyte of memory. So it's still a pretty decent number of pages. And then of course, so let's say it's 4 megabytes. That means we have 1,000 pages. Right, so how many comparisons do we have to make? It's 1,000 by 1,000, right? So now it's 1,000,000 page comparisons. And each page is 4 kilobytes. So now you have to compare the first word, the second word, the third word, and so on. So that's 1,000 words you have to compare for every one of those. So now we have 1,000,000 pages, and for every one of those, there's 1,000 comparisons, or maybe 512 comparisons in 8-byte words. And so you end up with 1 billion comparisons. It starts getting kind of slow. So in order to do a little better, you may want to use a checksum, basically, or a hash, I suppose. I called it a checksum here. I'm not sure. I think I was just tired. It should be called a hash, where you run through for when you want to do a comparison, when you want to do this dedupe, right? We compute a hash number for each page. A hash number is sort of a shortcut, right? It doesn't say for sure that the 2 pages are the same if the hashes are the same. Right? If the hashes are zeros, let's say, it says something about the contents of the page, but you'll still have to compare the entire page if the hash is the same, because of hash collisions. Anyone familiar with hashes and collisions? Right, okay, good. So the fast solution then is compute a hash for all the pages, then do the million comparisons, right? Because now you're just comparing hashes instead of entire pages. And if the hashes happen to be the same, well, then double check with a full-on comparison, because you will get collisions. And if you do, you'll have problems. Right. Yeah, if the 2 pages are exactly the same, then we'll want to point them to a single copy and make them both read-only. And then there was the copy on write bit. So I think that's about it for the homework. I think you'll find this one is easier than the previous one, because you've played so much with map pages and virtual memory and so on. On the other hand, we have a midterm in the way as well. So I think what we'll do is, the midterm is on the 12th, right? And we'll make the homework due the week after. So the homework, let's see, the midterm is on a Thursday. Oh, we can make it I guess we'll make it the Thursday after the midterm.
So that's
right.
the 19th.
The 19th, right. Yeah, it's probably best. But I'll make the template available. I think the template is fine now. I pushed it already. You can get started. But my solution didn't work. I was playing with it this morning, and there's one little something isn't quite right. So once I get the solution right tonight, then I'll update the template if any changes need to be made. Okay. So shall we dive back into the process switching and context switching? Or unless there are any questions on the homework or the midterm. Right. For the midterm, remember to bring the book printout. If someone doesn't have a printout, let me know, and you can come get one in the office. All right. So. I guess one thing that wasn't quite clear when we were what is this? Seems like it's the wrong drawings. Yeah.
The midterms in class, right?
Yep, it'll be right here. What is this? Oh, yeah, it's drawing from last semester. Shouldn't do that. F17. What's going? Aha, here we are. Okay. There they are. Good. So, all right. So before we dive back into this one, I wanted to make something a little bit more clear. And that's this, the difference between switching between processes and switching between a process and the kernel, so to speak. So, not actually sure how to draw this, but say we have a process A, and we have our process B. This will be their memory layout, perhaps. So up here we have a kernel mapping, and that's identical in both of them. And when we're running process A, CR3 here is pointing at this page table, right? This virtual memory page table. That's the virtual memory layout we have. So whenever we're running user code, we're running code that's down here. Here the permissions are user level permissions. You're allowed to access it, and also when you're running this code, you don't have the permission to run any privileged instructions. When we make a system call, we're not changing processes. All we're doing is we're changing our permissions, our privilege level. So now we're still process A, but we're running code that's inside the kernel mapping. What's nice about this separation here is that process A can't change the code in the kernel mapping, and it can't enter the code just anywhere. It can only enter at very specific locations, the beginning of the trap or system call handlers. So the process can't really change what the kernel is up to. It can ask the kernel to do things, but it can only sort of ask nicely. It can't make the kernel code do anything. And that means that even though we're running as process A, when we're in privileged mode, what we can do is very restricted. So we're running kernel code, but there isn't such a thing as the kernel running. Right? We're running, this is our process still. The process is now executing supervisor code, and there isn't just any supervisor code. There's very specific functions that you can run when you're running in supervisor mode. At some point, the process may decide, and that is actually when you're in the kernel, oops, I shouldn't do that. When you're running in the kernel, this code that is running as this process still, we're still at process A, may decide that, oh, it's time for me, process A, to stop running. Right? Even when an interrupt comes up, so you have your timer going off, process A was running some user code, a timer goes off, we're jumping into the kernel code, we're still process A. It's just that now process A decides my time is up. I think that's the best way to think of it. And then when it decides my time is up, well, then we have to switch. In part, we have to switch this one to here. But that's not enough, because we had a certain stack, like the process A was doing something in the kernel. It was doing something in user space. Those are two different stacks. When we switch from user space to the kernel, we already saved away our stack pointer from here. But when we're in the kernel running and we make that decision, well, now we're using a certain kernel stack. We're in a certain place in the decision tree, so to speak, in the kernel. And we need to be able to get back to there. Like, I decide for whatever reason I wanted to switch to a different process, but whenever we're done with that other process, I should come back to where I was. Right? And that's the proper context switch. So I guess this is a change of privilege levels. Usually it's a system call or an interrupt. And here we have our context switch where we're changing the page table at some point. There's no great hurry because look, it's the same kernel mapping in both of them. So as long as we're running in the kernel, we don't have to change the page table. But we do have to change what's our instruction pointer. Right? Once you switch over to process B, we need to be doing whatever it was doing. And we need to have the register contents that it had when it stopped running last time. And then finally, before we go from the kernel mapping back to running process B's userland code, well, by then we have to have changed our CR3 to point at the process B's page table. Okay, so I started drawing this elaborate thing, but we didn't quite, we didn't have time to kind of return to the drawing after we'd seen the code. I think we will need a little bit more of this drawing eventually, but just go like this for now. All right, so let's see. I guess we're having a timer interrupt. So the user program is running, it has some stack contents, it's running some program, it's doing whatever it's doing, and suddenly a timer goes off. When the timer goes off, the CPU automatically switches to the previously indicated kernel stack, which was indicated in this TSS, the trap switch segment, little special nook and cranny in the CPU. Okay, so the CPU knows where is the kernel stack, so we'll switch that, and it puts the instruction pointer, the instruction pointer, that's whatever code we were running, the previous RSP, that's to here, and the flags that were in the, there's a special eFlags register that keeps the carry and the compare bits and such. So it puts that in the trap frame, and after that it's up to us. So we're putting a bunch of registers in the rest, and this is in trap ASM. We get finally to trap, we go to yield, we get to sched, we get to switch. This is just basically, okay, we're deciding it is time to change to a different process. Right. In trap we said, oh, this was a timer interrupt. And then we're saying, oh, we have a running process. Well, if the timer went off, it's our turn. So we call yield, grab some lock or whatever, and then call sched. And sched finally calls switch. So we'll go through those steps in a little bit. Let's see. Oh. All right, there's the yield. Inside of our yield, we grab the p-table lock, and we'll be doing a lot of grabbing of the p-table lock. Basically, whenever you change anything in the process table, you need to hold a lock on it. Here we're changing the states, the runnable. We can't just do that without holding the lock. And also, whenever you enter sched, you're expected to be holding the lock. Sched says it's time to run the scheduler. Basically, switch to the scheduler. Let's see what's happening there. And here it is. So we're passing in a pointer to our, a pointer to a pointer. The context here is supposed to be a stack pointer. So we're saying, we're passing in, okay, write our current stack pointer to this place for later, so we know what our stack was like. And here is the stack that we want to be using. This is the previously, or the other running process, so to speak. But the scheduler isn't a normal process. The scheduler actually doesn't have a process ID. It's just a very simple function that goes around and around and looks for an available process to run. Actually, let's see how we get there. When we're first starting up our program, our kernel, in main, eventually we get to MP main. After we've created the first user process, we get to MP main, and this one eventually then calls scheduler, and that's the last thing the CPU does. That's the last thing the kernel does. So it gets to scheduler and it doesn't come back out of scheduler. It never really finishes here. So let's see what scheduler is doing. Oh. Here it is. So this one runs forever. It's a nice way to say while true. So we run through our process table lock, try to find one that's runnable, and then we switch to it, and then we come back. So the intent of the scheduler here is we switch into the process, and now we're running the process. At some point the process is done, then we come back here and we continue around the page, around the P table. So we're not starting from the top of the P table every time. You could imagine a scheduler that works some way like that too. There's lots of different ways to do scheduling, and we'll talk about various ways to prioritize processes and such later on. But basically this is the simplest sort of round-robin scheduler you could implement. All right, so coming back to switch, actually to sched perhaps. How do I look for sched? Sched. Here it is. All right, so that said, we were running the scheduler. Right? At some point, the scheduler switched over to running the first process. The first process got interrupted by a timer interrupt. We got in here, and it's time to get back to the scheduler. So let's see what's going on here. So now the current stack layout is like that. And actually, let's make a scheduler stack too. And this actually just has a context. I don't remember exactly what's in there, but it looks like that, and we'll see momentarily what's in it. All right, so this is the CPU scheduler, this thing. The CPU, just like proc, is a variable that's specific to this to this CPU. So there's one for every core. There's one proc and there's one CPU. We'll see how that's implemented in a little bit. All right, so CPU scheduler is pointing at this, and here proc context, that's just a variable. We don't need to worry about where it is at the moment, but we will be storing our current stack location to that eventually. So let's get into switch. Right. So now this is the context. So we got into switch and we save away a bunch of registers, all of these, and in fact, no, that's it. All of these are the context. So let's see. We got the switch stack frame already. That's what we got when we called switch. Sched called switch. It put the return address here. There was a couple of arguments. They're also sitting up here somewhere. If there are any local variables, there are no local variables for switch. They would be in here. And now we're starting to run switch. And now we're filling up with a few more things. Actually, what we're filling it up with is one of these contexts. So we'll just stick that at the bottom. All right, so switch is storing all of these values. It doesn't need to store any other values because there's a convention or sort of a promise by anyone that calls this function that if they had something useful in those registers, they would have saved it already to the stack. there's maybe one good reason you can think of for this. We're supposed to send our first argument in RDI, right? Our second argument in RSI, and then in RAX, and so on. Don't remember the order. But basically, we're supposed to pass in arguments in those registers. We don't pass in arguments in these. But so a function might expect then that those 6 registers, or 8 that we can use for, I think it's 6, that we can use for passing in values, well, it can use it for something else as well, right? These other ones are potentially holding something useful for the calling function, so we have to, if we want to use them, then we have to save those away. So it's half and half. Half of them are for us, half of them are for the caller. All right, so to respect the caller, we save all of these registers, and then, so now we have our context over here and our stack pointer pointing to there, right? And maybe we should do the other one too. Right. And then we say, okay, let's store RSP at %RDI. This is our first argument. The first argument is that proc context. Right? The address of proc context is in RDI. So now store RSP wherever that's pointing. So in the proc context. Okay, so now we have also a proc context pointing at it. That's for the currently running process. And then we're moving the second argument, which is an RSI, to RSP. The second argument was this, the CPU context. So we're changing this to be the same value as CPU context. We're not dereferencing it, we're just pointing to the same value. Whereas here we're storing RSP into whatever the RDI was pointing at. Okay, so now we have the scheduler stack over here. That's our new RSP. Oh, great. Okay, that's better. Coming back. Now it looks like we're running the scheduler. In fact, there's a little bit more here. The scheduler stack looks a little bit messier than that. So let's just fill that up a little bit. It should be at least main and then MP main the scheduler, right? That was a sequence of function calls. So it probably should look like this. Although if you look carefully, I think you'll find that main and maybe MP main and maybe scheduler are declared as no return somewhere, and that means that there isn't actually a call. So there's just a jump at the end. So you don't get an instruction pointer on the stack. You don't have a proper stack frame. You can reuse the stack frame. There's some little pieces there. So maybe these things don't actually exist up here. Either way, that's what we're, at least conceptually, it may well look like this. So now we're still inside RIP. We didn't change, right? So we're still here. But we're now running with this stack. So now we're popping these values off. And those are the old ones that used to be the old ones that got saved. Last time when the scheduler called this, we saved them, right? So they ended up over here. And now we're restoring all those values. So we pop all those off. this CPU context is actually going to keep pointing out here in space, but that doesn't matter. Our RSP automatically, when you run pop, increments. So now we're down here. And then finally there's the ret, which takes the instruction pointer from over here, the return address from over here, and that will bring us back into schedulers. This is a scheduler stack frame. Let's see, I don't know where you would if you would consider the return address as part of the scheduler stack frame. Probably not. Probably part of the switch stack frame at the very top. Well, anyway, now we get to return back into the scheduler. So we let's see. Yeah, here it is. Right. So we came in through the yield, and then we come out this way, and now we're suddenly running the scheduler. We go around, and then probably if there are no other processes running, now it's our turn again. Right? Our process was set to runnable, so let's just continue around this one more time and see what happens. So we go around here, and we find, oh yeah, our process is runnable. There were no other ones. All the other ones were, they were unused or sleeping or something. So ours became the next one to be runnable. We set the current process to P. That's just the entry in the P table we're at. Switch over to the correct page table. Say, okay, now we're running, because it's good to keep track of what we're doing. And then switch over. So let's go back into switch. So now this is the situation, right? We're in scheduler. We're calling switch. Let's do that. I probably should have drawn it this way last time too. Calling switch. Creating the context, right? Pushing all of these things on. This just decrements our RSP. But let's go back. See, now we're calling it with the address of this CPU scheduler variable instead. So we're saying, let's store our current stack pointer over here, right, for later restoring, and we want to switch to this context. So we're passing in, so we are passing in, okay, that wasn't it. Scheduler. The process that we want to switch to, right? So that's this one here. That's what we're passing in this time. Moving on. Okay, so we're storing all of our register values in this context. We are storing the current RSP, right? Remembering our current RSP value in the CPU context. So now we're pointing this, we changed that to point to the same place like that. And then we're taking the second argument and storing that in our RSP. So now, actually, when we do this, that's when you do that switch, that's really when you switch processes, right? That's where the context switch really happens. Because the stack is what keeps track of everything we're doing, and to a large extent, all of the register values that we had. So now we just restore all those values. This one actually didn't get updated. That was a mistake. I don't know how to fix that. Okay. Right, so that one is actually still pointing down here, but it doesn't matter because we don't. The proc context is not relevant right now. We're running that process. All right. This proc context and the CPU. Oh, that's called scheduler. It could just as well have been called context, right, or scheduler context, perhaps. Right. So we popped off all of those values, and then we have a return, which means we're killing this one. And the return got it back into sched. See. No, thank you. There. All right. So we returned. We get to in here, and that was in that stack frame. Then says, oh, well, we came from yield, so the next return will bring us back to yield. The next return brings us back to trap, and then from trap we get to trap ret. And then we're restoring all of the register contents from user land, and eventually we get a iret and return from the timer interrupt. Well, actually, it's not clear that we're returning from a timer interrupt anymore, is it? Well, in our case, that's what happened, right? Because we had this scenario where the timer interrupt went off, the process yielded, the scheduler just went one time around, went back to the same process, and then we returned. But you could imagine a scenario where we switched to a different process, and that process got switched out during a system call. In which case we would come in through a system call, enter the scheduler, and then return from an interrupt, so to speak. Actually, I don't know that I've run into this situation. I have to check that that is actually something that we handle correctly in the code. I think we are. Okay, questions? Who went through the code between last lecture and now?
In reference to this?
What's that?
In reference to this?
In reference to this, yeah, to kind of try to get it. Okay. If it's not crystal clear yet, make sure you do. We'll be doing a fair bit of task switching. It's good to get this straight. All right. So whenever we're running kernel code, there's really only two choices. We're either running on behalf of a process, or we're running that little scheduler loop. Right? That's it. There's no such thing as running the kernel. We're running the scheduler loop, or we're running interrupt handler or a system call handler on behalf of the currently running process. But one thing to keep in mind, perhaps, is that if you have a multi-core CPU, there's more than one currently running process. And so we have this variable. In fact, yeah, we have a few more minutes. Let's think about how this variable works. It's a really weird little variable. It's proc. Right? You assign to proc, and it stores the current process. Except there's multiple current processes. So which one is it? Right? Usually a variable has an address in memory. Right? So when you make an assignment, it says move, value to memory, or usually move from a register to memory. So what would the address be if it has multiple different values? If there's in a 2-core CPU, there will be 2 procs, 1 per CPU. And which address is it then? That isn't entirely clear. How do you get that mapping? So what we need is called thread local variables, or in this case, I suppose it's CPU local variables. We're not worrying about switching between processes here. We're only caring about which CPU are we running on. And so let's just see what happens when you dereference proc. Let's see, what's a good place to do that? Maybe right here. Actually, even simpler, maybe this one here. In scheduler, that's pretty good. So we're setting proc to 0, And it has to be this CPU's proc. So what's the assembly going to be? I think I may have mentioned this. I'm not sure. Anyone want to take a guess? So I would say it should be like move 0 to EAX, some register, RAX or some register. Move RAX to the address of proc, right? But unfortunately, the address of proc isn't just a straight up address. So how can we make it, how do we calculate the address of proc? Where does it get from? Where does it come from? So one might say, oh, we take, the CPU ID, use that as an index into some proc array, right? That might work. But where does the CPU ID come from? Is it a global variable? Not really, right? Because if it's a global variable, then there's only one CPU ID. So one could imagine, there's instruction, CPU ID that gives back a number between 0 and the number, of course, in the machine, and that would be great. But there isn't such a thing. Yeah.
Could it be saved somewhere on each CPU with their own ID?
That's a good idea.
Like their address is maybe, I don't know if it's hardwired or hard-coded or something like that, but it's saved in a permanent spot.
That would work. So if we can somehow store either an address or just the ID of the CPU somewhere, we figured it out once. And there's actually a way to figure out which ID you have. There's this whole LAPIC thing. If you look in the init, there's some init LAPIC, and there's all these different searching for this and that, and it's a big mess. But there's a way to find out, like, for each CPU, what's its current ID. So that's one way to do it. But where do we store it? Like, if we had this ID or an address where we want to keep our proc, essentially that would be even better, right? If you have a place to store, a CPU local place to store an address, well, just store the proc number there, this proc address. Use that, maybe. But where do we store it?
Is there a CPU cache for proc for each CPU, and you just dereference the same address and it's in the same spot for every cache?
Unfortunately, the processor doesn't know about proc. Proc is just another value. But we could keep it in, say, R12, and just not use R12 for anything else. That would work. It's kind of expensive, though. That's a nice register. We have a lot of good registers here. Are we going to waste an entire register, ban it from any other use, just because we want to keep our process ID in there, or CPU ID?
Does the CPU ID need the entire space of a register?
Well, a register is 64 bits, so even if you just use 2 bits of it, who's going to use the remaining 62
yeah,
bits?
I'm saying, like in this like 64-bit context, regardless of whether or not it's a register, does it need all 64 bits? Obviously,
No.
storing the address. Okay.
Right, it's okay with just a couple. If you have 4 CPUs, 2 bits will suffice. But nobody can find a use for the remaining 62 bits. You want 64 bits for whatever you're doing.
Okay.
Like if you're adding 2 numbers, you don't want some garbage 2 bits lying around in the number. It gets weird. But there's this other thing. It's the segment registers. Nobody's using the segment registers. There's a couple of them that are particularly unused. The CS and the DS, they're there for this vestigial use, I suppose, still to kind of indicate what the privilege level is and so on. But there's the FS and the GS, and nobody uses those for anything. But they still have to be there because if you're running, I don't know, 16-bit mode or something, you might still want to be able to use those. So they have them, and kernels have been using those for ages, and lately GCC caught on too. So let's see how it's declared. First, let's see. They can't actually remove the FS and GS because they were used for this purpose for quite a while, and if you just remove them, well, now they're going to have a lot of work to do on all the various OSs before they're portable, before they can run on a new CPU. So that's how we declare it, and you can do this yourself in any program. If you just declare it __ thread, now this is a CPU local variable. And the effect is if one CPU, or sorry, a thread local variable, but in this case it makes no difference because we're not switching GCC threads. If you're if you're assigning to this proc variable, and then you run some more code on a different CPU, it's still 0. Right? They look like completely different variables, but it's only accessible from the local CPU, or in a normal program from the local thread. Okay, so let's see how that's implemented. And this is always a good exercise. Take a look at kernel.asm. So this is not handwritten assembly. Right? This is very nicely dumped, or what do we call it? It's not a disassembly either. It's something GCC generated with a flag, I don't know what flag it is, saying like, oh, let's output every piece of C code and then see what assembly comes with it. This is from mboot entries. This is actually assembly, but let's go a little further down where we have some real C. Here you go. All right, so this here, PD0 equals size -1, well, it produces these lines of assembly and these lines of machine code. Good stuff. But now we can look exactly for our proc equals 0. Here. So here it is. In fact, we didn't have to put anything in RAX. I forgot. Well, we're putting something else in RAX, in fact. So in order to assign a 0 to a memory address, it looks like you can write an immediate to a memory address. I forgot that you can do that in x86. So we put immediate, we wanted to assign proc equals 0, right? That 0 is this 0. That's a -8. It looks like a big number, but it's a -8. And then we're saying, okay, let's assign to -8 in the FS segment. So FS here holds some sort of array for thread local variables. All right. And in fact, where is FS assigned? I don't know that. I should know that. Let's find it. Let's see. There. Oh, that's just 0. That's not good. I'll have to find that. That is weird. Yeah, I don't know where it's assigned. But but either way, this FS is pointing at a place that's local for every CPU. And it's in, let's see. It's actually pointing here. Let's see, where is it? Struct CPU. Ah, no, it's not anymore. That's right, yeah. There used to be a different implementation for these things, but with the __ thread, I don't actually know where it goes. So I'll have to look into this. It used to be like this. So we specifically or explicitly managed the FS and GS, but that's changed. Okay, I'll let you know when I figure out where the FS is assigned. Okay, so that's it for today. Take a look at the homework just to kind of get questions ready. And then I think the best suggestion for studying for the midterm is go through the pieces of code that we've been discussing in class, right? And try to understand what's going on in the code. When you find a piece that you don't get, you don't have to get all of the code. Like the file system stuff clearly is not covered yet, right? But the things that we have been covering and the functions that they call, take a look at that. If there's something you don't get, post on Piazza. Like, what's going on here, right? And we'll figure it out. And by the end, whenever everyone's following these discussions, then we'll all do great. So, that's it, and I'll see you on Thursday.